Combinatorics. So this is what we'll actually be doing a lot of in the curriculum. So has anyone, like, just out of curiosity, has anyone gone completely through section 11? Okay, good. Most of you guys looks like you haven't. You know, I saw a couple hands go up a little bit. Most of section 11 is going to be practice and stuff like this. I will tell you right now, don't stress out if you're like, oh my gosh, like, what is this? Like, I'm like, do we have to do this all the time? Is this all that data science is? This is a lot of just practice to kind of get familiar with the idea of event spaces and combinatorics. It basically is just advanced counting is like the way I like to describe it. Okay, so I have a few things in here. So first thing to talk about event spaces. So probability spaces, event spaces, basically it's just all possibilities when we talk about an event space. So basically, what are the possible things we can do? So with discrete numbers, you know, like this, like rolling a die, we can think of like saying, okay, we're gonna roll a die. If we roll one dice, what are all the different possible events we can have if we roll one 6-sided die? A typical like Monopoly die.
6.
Yeah, 6, which is the events themselves are either 1, 2, 3, 4, 5, 6, right? So 6 total ones. Easy peasy, right? So this is our event space. One die roll is just 1, 2, 3, 4, 5, 6. Easy enough, right? And like Jessica said, if you do len, I don't even have to do this, but why not? 6 of them, okay? So 2 die rolls, okay? Now, this might be one, like if you're familiar with, like, does anyone know what the different number possibilities you can roll if you roll 2 dice?
The first probability times the second.
36.
Yeah, so you can have, I think, first you said the first probability times the second one. It's not probability though, it's just a number of events, right? So the number of events 6 times the number of events 6. And the way you can think of it is like, I can roll a 1, a 2, a 3, a 4, a 5, a 6. And then for each of those roll, if I roll a 1, I can get a 1, I can get a 2, I can get a 3, a 4. So I have 1 paired up with 1, 2, 3, 4, 5, 6, or 2, 1, 2, 3, 4, 5, 6, and so on. And that ends up being 6 times 6. So total of 36, right? So what's really nice is in Python, it's like I don't want to count. I'm bored. I don't want to count stuff. I want to program. So you can see here, I just wrote a little for loop right here, or a nested for loop. So I have 2 rolls. So I want to count all the different event spaces. And I say, all right, die 0. So my first die, I count with 0 in die roll. So I'm going to go 1, 2, 3, 4, 5, 6. And then for each of those die rolls, I'm going to roll 1, 2, 3, 4, 5, 6. And then I'm just going to add this to a list, right? So you can see here in my list, it's going to be a list of 2 items. So for example, my very first die roll is going to be, or first event space would be 1, 1, right? And then I'll have 1, 2, and then 1, 3, and then 1, 4, and so on. Okay. So if I do this now, roll it, and we can see total of 36. And if I wanted to check out all my run rolls, there you go. So these are all the different possible events I can have. Okay. Sound pretty good? Yeah, it's all pretty like basic stuff, right? Okay, 3 rolls. So anyone got an idea of how I can make this? So I want to make this with 3 rolls now. Does anyone know, I mean, anyone got an idea what the number would be or how we would get that number?
6 times 36.
Yeah, 6 times 36, right? You have 36 different possibilities for 2 dies, and then you can roll 1 more die. So 6 times that. But of course, if you didn't know how to do that, one way we could do this is actually simulate this. How could we modify this code so we can say 3 rolls instead of 2 rolls?
Just add another nested for loop for die 2.
Yeah, so
and then
go ahead.
And then where you could do 3 rolls dot append, and then in there just add in the 3rd one.
Yeah, so I can do instead of 2 rolls, like you said, 3 rolls dot append, and then add that 3rd one, which is just in my case die 2. Yeah, and there we go. And I gotta change this now because this will be wrong. And boom, right? A lot more. And of course, 6 times 36, and got the number already. Some quick maths. 5, 4, 3, 2, 1.
216.
216. Good. Good timing. Okay. That's why we got computers, right? So you can see how this can add up pretty quickly and everything like that. So it's like, oh, cool. Like this is how we can kind of use simulations to kind of figure out different event spaces and stuff like this. And you can see here, I think I have the code just right here. Note that I said, okay, we can roll all 3 at once. So I note that I roll 1, 1, 1, 1, 1, right? And so on. You could also do roll 2 of these. So another way we could have done this is actually saying, oh, for every 2 rolls, right, we roll 2 dice and then roll a 3rd die. Okay, that would also work too. So just not, it should be the same thing. I just wrote it like this. So this would also, oops. Oh, dot append. Oops, I have a typo. There we go. Did I do this wrong? All right, I'll skip over because I'm not gonna. Oh, what? Sorry, everyone. Now I'm stuck in my code where I'm like, all right. So you can see that these all are the same thing. So you can think of it in different ways because they're all independent. So you can roll 2 dice at once and then 1 die, or you can roll all 3 individually. Okay. Cool. All right. So factorial. This is actually a really useful thing. Kind of quick. Give me a thumbs up if you're familiar with factorial. Okay, so I'm going to kind of go through this. So fun fact about factorial also is that it is actually not, well, okay, I'll go through a couple things. So firstly, basically factorial is n, like whatever number you want with an exclamation mark. So we could say that n factorial, 5 factorial, whatever it is. And basically it is basically saying, starting with the number, an integer, and you're just going times the next integer below it, the next one, the next one. So if you have 5, 5 times 4 times 3 times 2 times 1. Why did you put so many dots in here? I got excited with all the dots. There we go. So you can see 5 times 4 times 2 times 1. And so we can see 720. Factorial is a very fast growing function, just FYI. And note that basically if you try doing it, for example, in Google's calculator, I think I tried this out, is that you guys know you can do math in Google? Like you can do like 6 times 6 and gives you like 36. You can also do factorials in here too. So for example, if I do like 7 or 5 factorial, you can see 120, right? You can actually do, like I think I did 169 factorial. You can see, ooh, big number, right? I believe I tried this out. You can see I was really bored. 170 still works, 171, infinity. So basically it's too big because that's 171. So note that it's 171 times 170. So yeah, so it's gonna be even bigger. Google just kind of caps out on that because it's like, stop asking me questions pretty much. So anyway, it gets pretty big. But also fun fact is that even though we can use integers, we can actually use something called the gamma function. Has anyone know this about factorial by chance? So no? Ooh, good, fun stuff. Turns out actually you can define the factorial as something called the gamma function, which reason I bring up because I did it for my math bachelor thesis. I did a whole study on like the complex plane and the factorial. You can actually put in whatever number you want. Not every number works. For example, negative numbers do not work, but you can actually define factorial for like 3.2 and stuff like this and actually have real meaning to it. So you'll see sometimes in papers that's with this Greek letter is a capital gamma. So sometimes you'll see this a lot in discrete mathematics and probability. So anyway, fun fact. I don't know if it's fun, but it's a fact. All right, factorial, I'm just writing a quick function. There's a whole bunch of ways to write this. I'm not gonna go through all of it because you guys can find some really fun ways to write this stuff since you basically just looking at the previous one. But I made this a really quick one I can do. And then you can see my factorial 5 factorial computed to 120. Note that if you do 8 factorial, right, that's the same thing. So if I do 8 factorial, that is 40,320, right? Note that I can also just do 8 times 7 times 6 times factorial 5, and that's the same thing as me just writing factorial 8. So note that this can be really useful, especially when you're trying to simplify the mathematics and trying to basically divide things out. You can use this hint basically to make things a little bit easier. Okay. Cool. Note that this will not be able to go on forever. For example, you can see 25 factorial. Okay, still pretty big. But if I try doing 30 factorial, note that we start getting into weird stuff with computers. So you can see here is anyone, you would think 30 factorial is bigger, right? Thumbs up if you think 30 factorial is bigger than 25 factorial. Yeah. Clearly you guys are wrong, it's negative. So it's even smaller than everything else. So it's not because the numbers actually wrap around in the real world, it's because basically the computer gets so large, it can't fit it in the way it stores numbers anymore, and actually starts going into how to use negative numbers. So it's something to kind of be aware of when you're dealing with very large numbers like this. There are ways to make this accurately go through, but you have to be very careful. Okay? And that's why you see Google, for example, instead of giving you infinity, instead of giving you like this number, it gives you infinity because it's like, I can't store this anymore. Okay. Cool. Any questions, Factorial? Pretty straightforward. Understand? Yeah, go ahead.
So then what do we do if we want to calculate a larger factorial?
Good question. So one, my initial thing is try not to. So what I mean by that is that if you have, let's say, an equation that says something like, oh, we want factorial 100, and then it's going to be divided by factorial of 99, right? Right. You could calculate this whole number out. But remember, 100 factorial is what? Not the number, right? But it's 90 factorial 99 times 100. So if I had, oops, 1,000. So if I had it like this in mathematics, right? You can say, hey, I don't like I can just use the properties of division, right? To say, hey, I can get rid of factorial 99 divided by factorial 99, it should give me 1, right? And then it's just, oh, this answer should just be 100, right? But if I tried putting this in, just to kind of prove my point, factorial 100, and you can see it says a 0, which is clearly not true, right? So the reason why is because this is very large. So you can do certain things, like you can treat like something called doubles instead of integers. You can also do higher precision, but that will only get you so far. At a certain level, everything will eventually fail because you've run out of space to store things. So in general,
how about memoization?
I'm sorry, say
Using
that one time.
memoization with factorials.
You can do certain thing with like you can store some of the information later, but you note that like just like with just to kind of prove my point with like Google, the reason why they show you like 169, you'll notice that I don't have all the information here. At some point it can't store all the information it needs. There are really big systems that you have to deal with it, but they're like over 128 bits of information per number. So most computers are not meant to do that. You can do certain things. I will say like SciPy allows you to really get into deep and like, I'm trying to avoid like the whole computer science-y part. Yeah, my overall thing is like, if you can avoid large numbers, if at all possible, try to do that because that's the safer route. Because eventually you will reach a number that's so large that you literally cannot write it down, or the computer cannot literally hold it in memory. So yeah, makes sense?
So yeah, so is this something that we won't really run into often in data science, needing to use large numbers?
You probably won't unless you're doing something very scientific. This also applies for very small numbers. So if you have small numbers with very large, what's it called? Precision, like very, very like high precision, but very small numbers, you come off a very similar kind of thing. Maybe I'll share a video out later because I think there's actually a great like YouTube video about this mathematics and stuff, like why computers act this way. But in general, you probably won't have this in data science. And but you can run into this if you're not careful, which is like, for example, if I did this right here in my code, like this would run like you saw, but it's not going to give me the right answer. More closer example would be something like 30 and like 25, which we saw was like, oh, that's just basically 30 times 29 times 28 times 27 times 26, and that would be the answer. But you can see here, this is giving me a negative number, where in reality, if I did like 26 times 27 times 28 times 29 times 30, it's a big number, but it's manageable. It's not negative, right? So this is where like you have to be careful about these kind of things if you're just putting it in your code. Yeah.
Cool, thanks.
No problem. And good question. I think it's kind of something you kind of be aware of. All right. So I'm going to skip over real quick the sets. This is in the curriculum. So note that just like we have like list, we have tuples, right? We also have something called sets. Note that basically it's just the way to notate it is literally just like as if you're writing a dictionary with these curly braces and just kind of the 1, 2, let's say 35, 3 like this. And then this will be a set. So note that, and I can just type set A. And the reason why this is really nice is that we don't care about repeats. So for example, if I have like, oh, I have 1, 1, 1, 1, 1, 1, it's just going to count it once. It's like, oh, if it's either in there or it's not in there. So it doesn't care about like duplicates. Okay, and that works really well with probability. But I thought I'd just mention this really quickly. Oh man, I didn't think I was actually going to get through all this. I thought I was going to be able to get through all this really quickly. I feel really bad being the first one we have. But so the next part that we really have is permutations and combinations. So I had a little breakout that I guess we won't get into. But the main thing about permutations that I'm going to talk about is basically just saying how many different ways you can do things. Remember, probability really just comes down to counting, how we do counting. So a permutation, for example, is essentially like, let's say we have like, I like using like letters like A, B, C, and say how many different permutations can we have? Like, well, we can have A, B, C, or we can have A, C, B, or we can have, let's say C, A, B, and then we can have C, B, A, and then we can have B, A, C, and B, C, A. I don't know if I said the same thing twice, but this would be all the different permutations of A, B, C. And what basically it means that we count these things as separate. So it makes sense for like words, for example, like cab, C-A-B, and C-B-A should be counted as different things, right? Like those should not be treated as like the same thing. That's what a permutation. So that's when order matters, okay? So when you think of permutations, I want you to think order matters, okay? And so we can figure out how many different possible groups you can have. Note that I've said like, oh, instead of saying permutations of A, B, C, I could have said permutations of A, B, C, D, but only choose 3 letters. It's like, how many different ways can we choose 3 letters from 4 different letters? Okay, so that's kind of like what you would do permutations on here. And the way we can write this actually in formula is just this formula right here, which depending who you talk to and how they note it, basically this is doing a permutation for n items choosing, that's usually how I say it, choosing k things. So if we have 4 letters and we're choosing 3 items, 3 letters from that, this would be n equals 4, and then k would equal 3. So hence that little factorial in here. So if I did this, so with that whole example of like A, B, C, D, but only choosing 1, 2, 3 things, that would be 4 factorial divided by 4 minus 3 factorial, which is just simply 4 factorial over 1 factorial, which is just 1. So 4 factorial, which ends up being 4 times 3 times 2 times 1, which is essentially just 24 things. I'm not going to write 24 different things, but you get the point, is that you can do this part. And you can do this when order matters. Okay, makes sense? Cool, cool. Any questions on that? Okay, so just know that n is the number of things you start off with, k is the number of things you're taking from, and this only works for order that matters. All right. Going to the next thing, which is combinations, which is honestly usually what you'll probably care the most about, though sometimes you'll do permutations. Combinations basically says, hey, we want to do something, again, let's just say with, I'm gonna do something really small, like A, B, C, but we want to choose only 2 things. And basically, we don't care about order. So A and B is the same thing as BA, okay? And then we have like, you know, C and B, right? It's like that's the same thing as BC. And then we can also have A and C, which is the same thing as CA. So let me go BC. Okay, so this would actually be all the permutations, right? For 3 items, choosing 2. So just kind of check that. It's 3 factorial divided by 3 minus 2 factorial, which is just 3 factorial, which just ends up getting a total of 6. So you can see here, that's all of the different permutations, but combinations, we don't care about order, so it would only be 3. So the number of combinations would actually only be this portion right here and not the rest of these. And so essentially what we can do is the formula, like I like to tell people, is like, don't think of, like if you're gonna memorize something, memorize this thing and then say, but now we have to discount all the copies. So essentially it's just the number of permutations divided by k factorial. So how many things we're actually choosing. How many things can we possibly repeat? So we're getting rid of those parts. So you can see here, this would be 6, right? divided by k factorial. Well, k was 2. So we can see 2 times 1. Well, that means 6 divided by 2, or 3. So you can see total of combinations is 3. So that's really what the difference between permutations and combinations are. Important part is really understanding when you should use permutations versus combinations. That makes sense? Okay, cool. I do know this is usually something that gets people like, it's like, okay, like that makes sense. I can remember this formula. I can remember this formula. How do I actually use this? I think that's usually where people get the most confused, to be quite honest. So I know I'm a little out of time, so totally understand if you do have to go. But I did want to kind of show one example. This makes it a little bit easier to kind of deal with. I think I'm actually going to do this example here. Is that imagine you have a team of, you want to consider the different teams you can make of 5 with only 8 players. It's like, how would you do this mathematically, right? Well, in this case, does order matter? In this case, if you pick 5 people out of 8 people? No, right? We just know that there's 8 different people. Those people aren't the same, but there's 8 different people, right? So you can think of it saying, oh, like I like to think of it like letters because this kind of makes sense in my head. It's like, okay, we have A, B, C, D, E, what's that, 5? Yeah. F, G, H. Secret, I'm bad at counting. 1, 2, 3, 4, 5, 6, 7, 8. Good, I have 8 things. So these are my 8 different players, and I want to choose 5 of them. 1, 2, 3, 4, 5. So the simple thing you have to do is just combinations, right? So we have the, our thing for permutations, which is just n factorial divided by n minus k factorial. And forgive me for my writing. I would blame it's the computer, but it's actually me, divided by k factorial. And so essentially we just start replacing these parts, and you're like, okay, what's n? Show me with your fingers. Yeah, 8. I see some 8s.
8.
Okay, good.
Yeah.
Good. Good. Speaking also works. So we have 8 factorial divided by 8. And what's k? 5. Yeah, good. Cool. Sometimes I feel like I'm like in Blue's Clues, you know, when I don't hear any, like if you were just to look at me like talking, it sounds like I'm like waiting for the response. But okay, so we have this formula. So let's simplify this a little bit, right? Basically, this ends up being, we have 8 minus 5, which is 3 factorial, right? Which ends up being, I'm just going to try to write this over here. So 8 divided by 5 factorial, and then divided by 3 factorial. Okay, does everyone see how I kind of just reorganized that real quickly? Okay, and then what's cool about this, like, well, okay, we know this is 8 times 7 times 6 times 5 times 4 times 3 times 1, right? Which is simply saying, hey, that's just saying 8 times 7 times 6 times 5 factorial. Cancel this out, bring back to my teaching math days, right? So I have 8 times 7 times 6, and then divided by 3 times 2 times 1. So we get 8 times 7, someone go ahead and put this in the calculator or the computer real quick. 8 times 7 times 6 divided by 3 divided by 2. Oh, that's easy. So that's cancels out. It's 56, right? So we can have 56 different teams. So that's the answer right here. So that's kind of like how you would do this, like, you know, straightforward answer and stuff like this. The hard part is when you're like, okay, like I can only choose 3 girls. Like there's an example, I think, and then this curriculum. It's like, oh, we have 3 girls and 5 boys, but you can only have 2 girls and 1 boy on each team. How many teams can you do? All you have to do if they're in groups like this. So if we have like that, my scenario, 3 girls. So we're just using something simple like this way. I like to use like the red balls, but this is more considerate with the team. So we can say, okay, we have to have like 2 girls to a team and 1 boy to a team, right? The way you do this is actually 2 problems. You say, how many different combinations do you have here, right? So how many different combinations you can have? Well, if you have to choose 2 out of 3, right? We already saw a little bit how to do that. So like, so just kind of quickly looking at that is, well, we can probably see real quickly. It's A, B, B, C, C. We have 3 different possibilities, right? And then how many ways can we pick 1 boy of 2 boys? That's pretty easy. There's only 2 possibilities, right? So 2 possibilities. So the total number of possibilities, we can have 3 different groups of girls with 2 different groups of boys. So anyone got an idea what we do? Starts with an M or an X. All right, not an X, I don't know. Multiply it, right? Yeah, so we multiply them together. So there's 6 total groups that we can have. So that's how you treat these problems. If you like have like, where you're like, oh, I need to pick this many people from this group in this situation, they could be like red balls. They can be, you know, like different like genders of like, you know, players or whatever, or different, you know, heights of different players, stuff like that, like breaking it down into those parts. All it comes down to like, oh, it's going to be either a combination or permutation. That's why I tell you, don't just try to memorize this equation and think of like what to do. Think of literally how you would build this team, right? And how you would approach the situation. That's going to help you so much more than memorizing, to be honest, a stupid equation. Because this is not, first of all, I hate memorizing equations. I know I have physics background. Like I'd say like I have physics background. People say, what, you don't like memorizing equations? Because I mess them up because I can't remember specifically what exactly it is. And it's so easy to mess it up and then not realize you messed up. So it's more important to really understand how you can like build this up and then say, okay, what situation do I need this? Oh, it's a combination. Oh, it's a permutation. Okay, cool. All right. Guaranteed you guys will have questions about this. At least some people will. So feel free to share on Slack and stuff like that. If you bump into a problem, like, how do you guys approach this? Or how would you do this? Put it on Slack. Don't be shy. It definitely will help you out and it'll help others out too. Like I said, this is probability and combinations, permutations are really about counting, but it turns out counting can be really tough. So just know that, you know, you're on there, and I'll jump into, and sometimes I'll get stuck too. And I'm like, wait a second, is that right? So it can be tricky. But before I let you guys go, I just want to let you guys know, be safe and everything. Everyone who hasn't put a stand up, which is most of you, I'm looking at everyone right now, do a stand up, and then I won't scold you as much in the future. And then of course, if you guys haven't signed up for project assessments, make sure you guys do that. And I will see you guys tomorrow for Wednesday check-in. Just to be a good time to chat and everything like that. Hope to see more people this time, but totally understand if you can't make it. All right. Okay, everyone, take care and stay good out there.